Welcome back to the Chapter 8 of Multibody Dynamics using Altair HyperWorks, Motionview, MotionSolve. In this chapter, we will concentrate on the forces, some important functions like the BISTOP function, AZ and the WZ functions. So when you refer to the term force, it can be either applied forces or applied moments. The force elements that are commonly used in modeling in Motionview are the applied or the driving forces, the compliant connections such as springs, dampers, bushings and beams, the effect of the environment on the system like the effect of gravity, and last but not the least, the 3D contacts between the bodies. In this slide, I will highlight some important points on using different types of force entities in the MBD model. These rules are applicable to all the MBD software tools you use and not just Motionview, MotionSolve. Forces should ideally be smooth. Okay, what do we mean by this statement? This means that when you are modeling a force entity in Motionview, you must make sure that the force is continuous in nature. It is always from the solver perspective if you are solving forcing functions that are smooth and without any kinks. It's always better. So basically, the force function that you define in MBD model should not dramatically change with respect to the independent variables. Now let's move on to the force creation methods in Motionview. So I will show a quick demo in the graphical user interface. So the ways how we create a force entity in Motionview is by either right-clicking in the model browser and going to the add option and clicking on the force entity, and you can add any of these force entities. So this particular option is the force. We have the modal force, bushing, field, spring damper, beam, poly beam, 3D contact. So you can choose any of these options and say OK. The second method is if you have a pre-existing force that's already available, then you can right click on this and then just click on add force. And the third way is the most easiest way, to just add the force entities from the client specific toolbars. Okay, so just you have to right click on these icons and just say OK. So these are the three ways how you can create forces in Motionview. Let's go back to the presentation. So in these upcoming slides, I'll be explaining about some of the force functions that will be used in MBD modeling. I have concentrated on the BISTOP, AZ and the WZ functions since I'll be using these functions in our exercise 8. Forces can be added through expressions by using the expression builder in Motionview. Okay, now let's understand the importance of the BISTOP function and its application. The BISTOP function models a gap element. It can be used to model forces acting on a body while moving in the gap between the two boundary surfaces. This function can be used to limit the motion of a joint. So the BISTOP function has this particular syntax wherein the x stands for the independent variable, x dot is the derivative of this independent variable, x1 and x2 are the lower bound and the upper bound of the independent variable x, k stands for the stiffness of the boundary surface interaction, e stands for the exponent of the force deformation characteristic, c max stands for the maximum damping coefficient, and d stands for the penetration. The AZ and the WZ functions are used to measure the rotational displacement and velocity respectively of marker I with respect to marker J. So these are the syntaxes of the AZ and the WZ functions, wherein the arguments are I, J for the AZ function and I, J and K for the WZ functions. So I stands for the marker whose rotational displacement is to be computed, J stands for the marker with respect to which the velocity is to be computed, and K stands for the resultant velocity vector, and it is resolved in the coordinate system of the K marker. So before we close this chapter, I would like to briefly explain the approach used by the solver to arrive at the solution. MotionSolve uses the Newton-Raphson method to compute the solution. In this method, the non-algebraic equations are repeatedly linearized at a given time step to find the solution to a system of equations. This method may not be effective if the system starts too far away from the final solution. If this happens, the integrator may report that the solution is not converged and will go back and take a smaller time step, hoping that this time it will be closer to the final solution so that the Newton-Raphson method can converge. Okay, now I'll give you a quick demo on exercise 8.